Okay, so physics gives us optics, one of the main branches of physics, and optics are responsible for things like microscopes. So the microscopes that we tend to see in the crime lab are compound microscopes, so they have two or more lens systems. In our case, the two systems would be the ocular, that's the eyepiece, and there's either one or two eyepieces, depending on if it's a binocular or a monocular system. Or we may have two eyepieces because we have a comparison microscope, which is a type we'll talk about later on. So these are the type most commonly used in the crime lab, the compound microscope. Here we have a schematic, a picture of a compound microscope. It's not exactly the model that we use in the laboratory, but it's got the same sort of features. So you'll notice there's the eyepiece or ocular. That's where you would look through, and you try to look through with just one eye, and you don't close the other eye, but you try to keep it so that it's not interfering with what you see in the field of view. That eyepiece tube goes into the head of the microscope. At the end of the head you'll have the nose piece. The nose piece has the different objective lenses. So the ocular, the eyepiece, which is commonly 10 times magnification, will work together with the objectives, which are commonly 4, 10, and 100 times, so that you can get magnifications of 4 times 10 would be 40, 10 times 10 would be 100, and 100 times 10 would be 1,000 times magnification. Notice there's some stage clip there to keep the slide, the glass slide on the stage, and to be able to control it very well and not have it fall or have the sample move. You've got the aperture of the diaphragm that will allow a certain amount of light through. There's a condenser which also focuses the light in the iris diaphragm down below, and then finally at the bottom we see the illuminator, and that's part of the base, the bottom part of the microscope. On the sides we have the coarse focus knob, which is used at lower magnification, and then the fine focus knob, which is used at the highest magnification, or if you're at low mag and you need just a small bit of movement to get the sample crisp. And finally, the last piece to mention is the arm. The arm is what's used to carry it along with the base. So one hand on the arm and one hand on the base whenever you're carrying a microscope. Here we have a little more detailed depiction of the eyepiece. It contains the ocular lens, which commonly has a magnification of 10 times. And then if you see in figure 1 there, you've got really a system of lenses in there, and just some rubber eye cup and different housing to protect those lens systems. The other lenses responsible for magnification are the objective lenses, and there's usually more than one. So in our case we tend to have 3, and so they would be 4 times in this image, 10 times, and 40 times. So ordinarily with a sample that you would like to investigate, you'll have the 4 times lowest magnification objective lens coupled with the 10 times ocular, gets you 40 times overall, and that's the easiest to work with. Then when you get the sample centered, you can have then an increase to maybe 10 times objective, which would be 100 times overall, or 40 times objective, which would increase to 400 times overall. Earlier I mentioned the 100 times objective lens, and we don't see it in this system. Some of our scopes have it, some don't. That's used for immersion oil, so that's not commonly done with us, but maybe in the crime lab setting it would be a more useful tool. So there is a 100 times objective, but that's only used for immersion oil, and we don't do that particular technique in our laboratories. So you have to be careful when you're working at the higher mag, like 40 times, or especially at that 100 times objective. You have to be very careful not to crack the lens, because if you use the coarse adjustment, it's very easy to crack the lens. The lenses are quite expensive, so it's best to always use fine focus, fine adjustment at higher magnifications to prevent that issue. And again, like I've been saying, and we'll practice this in lab, you multiply the ocular lens by the objective lens to get the total magnification. So you should always be very clear whether you're dealing with 40 times total magnification, like we see in this example with 10 times ocular and 4 times objective? Or are we talking about the 40 times objective and we still have the 10 times ocular for 400 times total mag? So just be careful whether you're saying 40 times objective mag or 40 times total magnification. In certain cases, you don't need a lot of magnification. You just need to be able to see something, maybe a larger sample that wouldn't permit light to transmit through it, that you need magnified. So the stereomicroscope does a nice job of magnifying things just a little bit, but giving you a lot more detail, just beyond what the human eye can see. There's a whole world of detail available. So the stereoscopes are typically used to screen objects for trace evidence. So looking at the object under the stereoscope, again, it's a low mag, but it might be just enough to pick up that there's a hair or a fiber or a small spatter of blood on a sample that you might have missed it with the naked eye. It's also, as the name indicates, it gives a good three-dimensional view, stereo view. So this is really nice for, it's also known as a dissecting scope. It's nice for being able to manipulate a sample and do fine work that might be difficult to do without the assistance of the stereoscope. You could put a large image. You can see that it's a few inches or more that you have for what we call working distance between where the lens system ends and where the base of the scope is. So you could easily fit an object like a cartridge casing under the stereoscope to investigate for striation patterns, or just to look at the firing pin impression with greater detail. Lots of things that might have trace evidence would be useful for the stereomicroscope, but not able to be used in the traditional light microscope, where you need a very thin sample that allows light to transmit through. The comparison microscope is very commonly used in ballistics analysis, and it's really two compound microscopes with their ocular lens systems combined, so that you can look at it with binocular vision. So one eyepiece for each scope, so that's why you have the two different eyepieces, but you can look at them through your two different eyes at the same time. So the left eye would see the image on the left compound microscope, while the right eye would see the image on the right compound microscope. And this is, as I've mentioned, very, very useful for analyzing firearms evidence. So cartridge casings, for instance, you'll be able to compare firing pin impressions. For bullets, you'll have striation patterns. For tool marks, you'll be able to compare a tool mark recovered at the scene with a known sample from that same tool and see if the tool marks are identical. So this is very, very useful. It still relies on human beings. There's a human expert that will analyze the samples and give his or her professional opinion as to whether the samples were made with the same weapon or implement. But it's a really, really powerful technique, and it makes use of the compound microscope, but also the fact that we have two eyes and we can be looking at two different samples at the same time and comparing them. So finally, for micrometers, or a microscope, we've included the Microspectrophotometer. That's a mouthful. And it's really a compound microscope attached to a spectrophotometer. This is an instrument that analyzes light from a specimen. So if you've ever tried to donate blood, they'll typically use a spectrophotometer to test for hemoglobin, iron levels, based on the hemoglobin complex that they can use a very simple tool to detect if the levels are sufficient, or if your iron's too low, then they'll decline you as a donor until your iron levels improve. This technique is very helpful for the analysis of fibers and inks. So if we think about question documents, there we're commonly concerned with inks. Are the inks a match for each other? Has the document been altered after the original inks? Are the inks even the right inks in use at the time that the document supposedly was generated? These are all questions that microspectrophotometers can help answer, because you can focus with the microscope on a particular part of the document or the fiber sample or whatever it might be. And while you're focused on that part in the microscope, you're also analyzing it for its spectrophotometer's profile to see if it matches the ink from another part of the sample, or if it's a new, different ink. That can often be helpful in determining that the document's been altered or fabricated entirely.